Hello students, welcome to Kaggle Class of Physics classes. Today we will study Newton's laws of motions. Okay, and another video of the projectile part 6, part 7, part 1. I will give you later, but some students demands to give some videos about Newton's laws of motions. So I start here Newton laws of motion, the part 1, first video of the Newton, and we will discuss the second law, force equals to ma. In different cases, you already know in class 9, 10 or 11, 9, 10, already know the Newton's laws of motions, force equal to ma, inertia law, etc., etc. But in projectile, we already read some concept about reference frame. Reference frame is divided into two types, inertia and non-inertia. Inertia means acceleration of the system is zero and there is no any pseudo force. Okay, and non-inertia means acceleration of the system is not equal to zero, and at that time we get some pseudo force. Just like a merry-go-round or giant wheel, whenever a person rotates in a giant wheel, at that time person experience some weight loss or some weight gain. When the person descends and he experience some weight loss, and when the person moving upwards in a giant wheel, he experience some weight gain. Just like in lift, when lift is moving upward, weight is gained by the person because due to pseudo force. When lift is moving downwards with some acceleration, person loses some weight due to pseudo force. That's the application of non-inertial reference frame, and it is called the pseudo force because at the time weight means the mg is not the weight. Here normal reaction is the weight. So whenever in the lift, body is moving with acceleration a downwards, and mg here, suppose inside the lift body is here, and we get another normal reaction here. Okay, so mg minus n equals to ma, and you see just n equal to mg minus ma. So this is not the weight, this is the weight. So this is weight, apparent weight. So apparent weight is not equals to mg due to pseudo force. So this type of pseudo force already you know in the lift cases or in the different type of giant wheel or merry-go-round. Our centrifugal force is also just like in merry-go-round whenever it is it rotates in a horizontal plane. But now I will give you some example about the force equals to ma. I will give you some example about force equals to ma. At first, I will give you the basic knowledge of this Newton's second law in the rope. How can we apply Newton's second law in the rope? Suppose this is a rope of length L and mass equals to m, and if we apply the force here, and suppose rope is placed on the frictionless surface, mu equals to 0, and we apply force F here, and the system moves with some acceleration F equal to ma, and we get acceleration equals to F by m. But now if you want to find the tension at a distance x, suppose you want to find tension here, how can you find? Then just find this mass m dash. Find this mass m dash. The length of this part is L minus x. L minus x. So m dash should be m by l into L minus x. Now find the free body of m dash. If you find the free body of m dash, the tension is the main cause for acceleration A. So T equal to m dash A. T equal to m dash A. Just you get T equal to m dash A. And m dash is m by L minus x, and acceleration means f by m. So we get the tension here m by L into L minus x into f by m. That's the concept. So mass, we just cancel it. So tension equals to Fl by L minus Fx by L. So y equals to mx minus mx plus c. This type of graph you get from tension versus x. If you draw the graph tension versus x, then this we get y equal to minus mx plus this type of graph. Okay, you find it. After all, tension becomes 0 because at that end, when it reaches at the end, the tension, no tension because no mass is present here. This is the concept coming from Newton's second law or from the coming from pseudo force concept, because rope is moving, rope is not in a self-reference frame. You want to find the tension here inside the body, and you just take this body is moving with acceleration A, so it experiences pseudo force here. If you consider here then this tension is produced to balance this pseudo force. So tension is nothing but M dash A. Okay. Okay. It may be some difficulties present whenever two forces are present. Suppose two forces are present. Here F1 or here F2. Two forces are present. Okay. And F1 greater than F2. And mass of the body is M and length of the body is M. Again you want to find the tension and the distance X. Same question, but only different is two forces acts here and F1 greater than F2 and this is the mass M. So in similar way we solve the problem, but only difference is when we find the acceleration we apply two forces F1 and F2 and the resultant of F1 and F2. So acceleration equals to F1 minus F2 by mass. That's the first concept. And second concept M dash A. It is a similar fashion. T, second concept, free body of M dash, free body of M dash. That is T and that is F2. So T minus F2 equal to M dash A. That is the difference from the previous one. That is the difference. Initially T equal to M dash A, but now T minus F2 equal to M dash A. And now putting the value of acceleration and M dash, you get the tension. So this is the first example for the Newton's second law, and you can find the tension inside the body. You can find the tension inside the body. Okay? And we came to know that normal reaction is the true weight or is the reading of the spring balance or reading of the weighing machine. Whenever any person wants to know its weight in a weighing machine, the normal reaction exerted by the weighing machine is the true weight of the persons. mg is the true weight with respect to gravitation, but on that frame, n is the reading of the weighing machine. mg is not the reading of the weighing machine. Just to give an example, yes sir. How normal reaction shows the reading of the weighing machine. Suppose a box is here and a weighing machine here. This is the weighing machine, and a person stand here. Okay. And suppose this box is hanging from this ceiling and this rope, and the man pulling this rope with his hand to balance himself and also the box. Suppose the weight of the box is M and mass of the man is M. Okay, so man is inside the box and man pulls the rope to balance itself and the box, and the weighing machine shows us the reading. That means weighing machine reading is the weight of the man. And how can you find the reading of the weighing machines? Very interesting application of Newton's second law. It is in equilibrium because there is no acceleration. So you can apply Newton's second law. Whenever force equal to 0, acceleration 0, and it is equilibrium. That means all the forces. Equilibrium means summation of the fx equals to 0, or summation of fy equal to 0, or summation of fz equal to 0. That is called equilibrium, linear equilibrium. And for rotational equilibrium, tau x equals to 0 and tau y equals to 0. Tau means torque equals to 0. Moment of forces are 0. So that's the equilibrium concept. Along x-axis force must be 0, along y-axis force must be 0, along z-axis force must be 0. With respect to x-axis torque equal to 0, with respect to y-axis torque equal to 0, or with respect to z-axis torque equals to 0. This is the concept of equilibrium. Whenever we say the system is in equilibrium, you can find two kinds of equilibrium: static, dynamic, or you can find rotational equilibrium. Okay. Now here from this kind of equilibrium, that means vertical equilibrium. Draw the free body of the man. Man free body is just like mg. Man and the weighing machine exerts a normal reaction on the man, that is M. And man exerts a force that is produced tension. So there must be some another reaction force tension on the man. Okay. So n plus t equal to mg is the free body of the man. N plus t equal to mg is the free body of the man. And now the weighing machines concept. Weighing machines mg. That is here mg. And man exerts these normal reactions and the tension, that is, so for t equal to n plus mg. That's the concept of weighing machines, and this is the concept of man. And we find the n. If we find the tension here, if we put this tension here, then we get n plus mg equal to small mg. So 2n equal to small mg minus capital Mg. Okay. So n equals to m minus m into g by 2. That's the normal reactions you get. And this is the reading of the weighing machines. Okay, clear concept? That is the reference frame. It is a different kind of reference frame because man is inside the box. Box is the reference frame here, but box is not accelerated. And if man exert excessive force greater than tensile, suppose here man apply this tensile force, so it is in equilibrium. But if man exert extra force, then total system will move upward with acceleration A. So only the equation will change something. Equilibrium will not present, so force equal to ma. The resultant force equal to ma. You can apply this equation and you can solve at that time that again reading of the man. Again you can find the normal reaction. Okay. There is the second example. Second example of this. And a third example. I will give you third example. Very interesting example third. Suppose a balloon. A balloon is moving. Suppose balloon carrying some weight here, that is capital M, and balloon is moving downward with velocity v. Okay, in here. Suppose here resistance present, buoyancy present. Suppose buoyancy equals to b. Buoyancy means air buoyancy. Buoyancy means one kind of upward force, and that is directly proportional to V merged into rho L into G. That's the buoyancy formula. You know it from 9 concept, because in 9 you know the fluid mechanics. So buoyancy equals to Vi into rho L into G. Vi is the emerging volume, rho L is the density of the liquid, here density of the air, and G is the G. So first force is buoyancy. Buoyancy always apply upward direction. Number 2, mg, gravity, and number 3, retarding force. Retarding force means that is Fr. Fr, force is directly proportional to V, suppose, so F equals to minus kV. That means the direction of velocity downward, so force is in upward direction. So resistance force is upward. And mg, and suppose system moves with constant velocity V, so acceleration 0. So again system is in equilibrium. From the Newton's second law, if there is no force, no acceleration. So no acceleration, no force. That means it is in vertical equilibrium. So we can write mg. So that is mg downward, buoyancy upwards, resistance force also upward. So mg equals to resistance force plus buoyancy. That is we get. Okay. The balloon is moving downwards. Now some mass is some mass. Suppose some mass from the balloon is thrown into the atmosphere. Okay, some part of the mass, suppose small m, is thrown from the balloon. Thrown means just fall, just release from the balloon by man or by some other ways. If you release some mass, not without giving any velocity, just you release some mass from the balloon, then balloon start to move upward. Balloon start to move upward. Let's totally change its velocity v when the mass decreases to m minus m. So now m minus m into g, because this mass, you just release this mass from the balloon. You just release this mass from the balloon. Okay, without giving any velocity, only you release this mass. So mass decreases, so m minus m into g, now downward force. Buoyancy is already present, but velocity changes from downwards to upwards. So resistance force changes direction, and that is Fr. So now m minus m into g plus resistance force equals to buoyancy. Buoyancy will not change because buoyancy depends on volume, density of air, and g. So buoyancy will not change. Buoyancy is the same. Resistance force also same value because velocity, resistance force only depend on velocity, and with same velocity it moves upward. Initially it moves downward with velocity v, but now it moves upward with same velocity. So resistance force also not changing. Only weight, that is gravitational force m minus m into g, because some mass is released from the balloon. So you get the second equation, and this is the first equation. And if you find buoyancy or resistance force here, and in putting this resistance force here, suppose resistance force, you find the resistance force and putting here M minus M into G. Resistance force here means capital Mg minus buoyancy. Okay, then you get, that is the buoyancy. So you get this small mg. Small mg equals to 2b minus 2mg. Okay, that C is the small m. So value of small m you get, about we get from this concept. This is the third example of the Newton laws of motions. Okay, that is the example with respect to buoyancy, with respect to resistance force, and weight. Some mass is released from the value. Okay, now there is a from Newton's second law, force equals to ma. You know Newton's have three laws. Number one, inertia. Number two, force equals to ma. There is measurement of the force, and the number three, action equals to reaction and oppositely directed. That means no single force can exist in this universe. That is the Newton third law. And now another kind of force is also present in the Newton. The most important force is normal reaction. Normal reaction is very, very important. Normal reactions. Okay, just like a body is placed here, that is the normal reaction. Okay, it is most valuable part in the Newton laws of motion. Normal reaction. I will give you some example. Just normally, if you find normal reaction, you get the answer of the different type of question. Just like three bodies are moving. Suppose three bodies are moving. Suppose it is 3 kg. Suppose it is 2 kg, it is 3 kg, or it is 5 kg. Okay. If some force is applied here, suppose 200 Newton is applied here. Okay. Now just find the normal reaction N1 here, and now find the normal reaction N2 here. How can you find the normal reactions? Now that, suppose force equals to 5 plus 3 plus 2, that is 10A. So acceleration equal to 200 by 10, that is 20. Now N1 is the pseudo force experienced by these two forces. M1 is the pseudo force experienced by these two forces, these two masses, 3 plus 2 kg. So N1 equals to 3 plus 2 into A. Itna ho jayega. So N1 you get this. And N2 equals to, that is pseudo force experienced by these masses. Okay, these masses and these masses. Okay, so N2 equals to 2 into A. N2 equals to 2 into A, and you know that accelerations, so you get the normal reaction. That is the first free example of Newton's about the normal reactions. And now I will give you some another example about the normal reactions for different shape of the body or wedge system or different kind of body. Suppose this is a wedge or two body are shaping like triangle. So if it is theta, M1 and M2, and now suppose if you apply here F1, okay, and system is moving here. System is moving with acceleration F1 equals to M1 plus M2 into A. System is moving with acceleration A. That's mean here this is A. Now here you get the normal reaction in this way, NN. Now you get the normal reaction here in this way, NN. Now consider one of the body, M1 or M2. Which body will take? If you take M1, then if you take M1, then M1 means this body M1. Here normal reaction is here. If it is theta, okay, this is M, this is force, acceleration. So if you get the component of normal reaction, that is theta, so this will be 90 minus theta, so this is theta. So this is n cos theta and n sin theta. This is n. So n sin theta, this is n cos theta. Okay. So F1 minus n cos theta equals to M1A. And now putting the value of A, again you just find a normal reaction. Okay. This type of wave system with some angle, maybe theta, maybe 37, maybe 53. Okay, so this kind of normal reaction you find here. And another we'll see here, this kind of normal reactions. In the next part of the video, I will see you this kind of normal reactions. Whenever body is applied by force, what is the normal reactions? You will find here, if it is mass m and friction is 0. In the next video, we will start different type of problem with respect to normal reaction. So this is the first video of the Newton laws of motion. I introduce only Newton's second law of motion. Okay, just like my videos and subscribe the channel. Okay, thank you very much.